Yes, I used a power rule on x squared because this 2x completes the chain rule for this part of the problem right here, right? Derivative of outer function, right? I'm just looking at this little subtask, right? So the derivative of outer function cos is negative sign. Keep inner function same, and then take the derivative of inner function and multiply it on there. That's what the rule is, right? That's what I erased it. The thing I erased was trying to say in English, right? Take derivative of outer function, leave inner function inside. Take derivative of inner function, multiply it onto it. That is chain rule. Oh, we're supposed to do second derivative. Oh, shoot. Second derivative.
You wish to do the same thing again, wouldn't you?
I sure am. I'm going to do the same thing again. So especially when taking higher derivatives, it's a good idea to simplify. Yeah, this expression is going to be really, widely, right? So simplifying it first is a good idea. So now we take the derivative of this. So we can take d dx of the negative 2x squared sine of x squared plus the cos of x squared. Okay. So what's the most outer thing happening this time? It doesn't impact the problem so much, but what is it? What's that? Not the product, actually. This is the sum. This sum is actually the most outer thing happening in this problem. But because you don't even think about taking derivatives of sums. You just do it. You know what I'm saying? I take the derivative of this piece, I take the derivative of this piece. You don't really think about it that way. So the more important thing is what Justin is saying is this guy here, what's the most outer thing there? And it is the product of the negative 2x squared and the sine x squared, right? That's the more important feature of the problem. So we have d dx of the negative 2x squared sine of x squared. You do that. And we know that we can just add to it the derivative of the other one. That's why you don't think about the pluses being that significant in these problems. You know that's true. That's the sum rule for derivatives, right? All right, now we got this product. So the left-hand side is a product rule, and it has a chain rule inside of it, just like the last one. So first is the negative 2x squared. So we have negative 2x squared times the derivative of the second, which is the sine of x squared, plus the second, the sine of x squared, times the derivative of the first. Yeah, I know you guys know already, but I'm going to try it this time. And then over here, plus, we're not going to do anything with it yet, plus the derivative of cos x squared. Okay. So there's the expansion of our product rule. Without any derivatives taken within the product rule yet. Okay? Just the product rule itself. Now we'll tackle each of these little pieces. So and now these two should be quite similar, right? We did it a second ago, didn't we? What's the derivative of cos of x squared? We know this one. What's the derivative of cos of x squared? We did it right here, didn't we? Isn't it this? We did this little piece a second ago within that problem, right? Okay. By the time I let you know that it's already over there, we kind of figured it out again if we wanted to, right? But whatever. So we know this is going to be negative 2x sine of x squared. So that part's done. So now we have to worry about this. So negative 2x squared, the derivative of sine x squared is going to be cosine of x squared times the derivative of x squared. It's a chain rule on this little piece, right? Which we know is the 2x, given these two x's from the x squared. Plus sine of x squared. The derivative of negative 2x squared is what? Negative 4x. So all we have left now, just extend that minus a little bit. All we have left now is this little piece right here, which you know is 2x. Now I'll go ahead and combine that 2x with the negative 2x squared out here, right? So we know this is 2x. So we get negative 4x cubed cos of x squared minus 4x sine of x squared minus 2x sine of x squared. So now what's the last step? Yeah.
Can't you combine it?
That's right, it turns out we have like terms. So it'll be a negative 6x for this last part. So negative 4x cubed cos of x squared minus 6x sine of x squared. Again, we're just taking derivatives. We're doing no further analysis beyond the derivative. We're not saying equal to anything. We're not, we haven't found a tangent line in this section yet. Right, we're just finding slopes of the curve. That's all we've done so far. But just very complicated because of all these links in the chain. So now, for instance, let's say they said, find out, I'll just say over here, where is this equal to 0? I don't know where this is equal to 0. Because these are the types of questions you'll be expecting very soon. Where is this equal to 0? We had one the other day like this, right?
That function tells you where the derivative is at, what the rate of change at a certain point is at.
We had to be careful. This is actually a second derivative.
Oh, so that's the second derivative. Okay, so the rate of change is 0 at a certain point. So wouldn't that just be the y intercept?
No, not necessarily. This is the rate of change of the rate of change, right? It's the second derivative. Rate of change of rate of change. It happens to tell you about concavity of the function. That's what it really tells you about concavity. This is the acceleration of that thing over there, right? Second derivative is acceleration. Okay, if you want to think about it in terms of position, velocity, mumbo jumbo. So you want to know the acceleration is 0. That's what we want to know. When is the person not accelerating? When they're in my class. What's that? What'd you say?
I was gonna say, don't you plug in 0?
No, don't plug in 0. I want to know what x's make this expression equal to 0. Maybe 0 works. Well, I think 0 is an answer, but it may not be the only answer.
Graph it?
What did you say?
You graph it?
Oh, I missed it. No, you would not graph it. God forbid. You've got to solve this equation.
How?
What do you mean how? That's what I'm asking you.
Would you move one thing with the other side?
No, don't do that. Don't ever do that. Hold on a second. You got an equation equal to 0.
Would you factor it?
Yeah. Yeah. What does it mean when you have two things multiplied? Okay. Yeah. If you have two things multiplied equals 0, what does that mean? What does it imply?
One of them has to be 0.
One of them has to be, and perhaps both are, right? That is called the 0 product rule. So A equals 0 or B equals 0. This is the glory of the number 0, and why we even like to factor in the first place. What do you have down here? Are you multiplying things together? Nope, I'm subtracting. So is there any fantastic rule for A minus B equals 0? I guess A equals B. That'd be like moving to the other side. That doesn't really help you in terms of solving this problem, because I don't know what x is. I already know that this piece must equal this piece. I'm subtracting them, I got 0. I know that. That didn't get me anywhere. I'm trying to find x, right? So what you're always trying to do with factoring, you're trying to change adding and subtracting into products, because a product equals 0 implies a further thing about these functions.
So
right?
would you factor the first and then the second part, or everything?
Well, what do they have? What do they have in common?
X.
X, how many?
1.
Anything else?
Negative 2.
-2. All right. So take out what they have in common. Negative 2x. So what do you have left now? We have 2x squared cos of x squared plus 3 sine of x squared. So here is Rosales' answer right there, right? There's his answer, 0. Comes out in the factorization, right? This automatically implies that x must be 0, which you can